and then the nomenclature you can't get rid of. So let me cut this problem out. We're gonna work it. Make some room to work it. Let me put a page in. Oh shucks, I'm in the wrong. Hold up. In the wrong note. Yeah, we're good now. Let me add a page. All right. So let's work on this top problem right quick. And we're going to balance it. And this is an example of a question where we have, so this is, what's the date? 21st. Man, this time is flying by. All right, so we're still working on balancing and writing equations, which we'll do in a second, because we're going to work on some more of these word problems too. All right, so in this problem right here, remember I said, I think that was Thursday when we were talking. I said that there's some cases where you want to keep your polyatomics together and not just balance atom by atom. And this is a case where if you look here, you can see the polyatomics are the same on both sides and they don't change. All right, so for this particular example, we're going to balance the entire polyatomic and not just balance atom for atom, right? So here we're going to have on the reactant side, right, we're going to have H, we're going to have sodium, we're going to have SO4 and NO2. So we're going to keep those polyatomics together. This is a kind of a nuanced strategy. Most of the time when you balance an equation, you want to just balance atom for atom. But in this case, it'll be more efficient just to keep the polyatomics together, right? And that's not soy, by the way. Let me fix that for. Hold up. I tricked myself out of that by writing that out. That's all right. So it's SO4 and NO2. All right. So we have two hydrogens. We got one sodium, we got one SO4 and one NO2. Everybody okay with that? And then on the product side, right, we have one hydrogen, we have two sodiums, we have one SO4, and we have one NO2. All right. What do you want to start balancing first? We can balance, because if you look at the NO2s and the SO4s, they're both already balanced. So we could start with either hydrogen or sodium. What do you think?
Hydrogen.
Okay. How would you balance hydrogen? Looking at the left side and the right side, you got two hydrogens on the left and one on the right. What would you do to balance it?
Do you just need to put a 2 in front of the one on the other side?
Put a 2 right here.
Yes, sir.
Okay, so that's gonna increase this by 2. So it's gonna be 2 hydrogens. It's also gonna increase this by 2. Right now, we can balance the NO2s now because that got affected when we put that coefficient in front of hydrogen. So on the other side, where you have sodium nitrite, what would you do? I saw something in the chat. I'm not sure what to do about that. Are you using the Word document or the PDF? That may be the issue. Yeah, that might be the problem. Hold up one second. I can upload this to the chat as a PDF. Let me do that right quick. Let me find it. I want to say is this one. Try the PDF I just uploaded to the chat. All right. So now we have we're going to put a 2 here, and that's going to give me 2 sodiums, and it's also going to balance the NO2s. So now if you look at both sides, you have 2 hydrogens, which is good, 2 sodiums, 1 SO4. It's all right. 1 SO4 and then 2 NO2. So that is now balanced. So the coefficient of 2 in front of sodium nitrite balances that, and the coefficient of 2 in front of the nitric acid on the other side, or nitrous acid on the other side, balances that. All right. Any questions about that example? All right. So let's do one more. Let's do the one at the bottom. Let me see if I can move that over. Crap. All right. So you can't see the document I just uploaded, Haley?
No, I don't see it in the chat.
I don't know why. Hold up. I have to send it. Let me pause this recording right quick. The second problem, where we have CO2, water, and then C6H12O6, followed by oxygen gas. All right, and so this, in this example, and let me put up here. I neglected to write this in. So if your polyatomics are intact on both sides, can balance them as they are. I know I mentioned it not Friday, Thursday. I said you have to look for when you can do that. You do it when you can see both the polyatomics in the reactants and the products. Then it's okay to just leave them whole and then just balance them that way, like we just did. Let's do the second example. So over here we got carbon. We're going this you can't. You have to balance atom by atom simply because of how the everything gets added together. So nothing is the same on the other side. So the reactants add together and then you get all of this weird stuff on the product side. So you got to balance it as it is. So we're going to take it and break it up. So carbon, hydrogen, and oxygen. And over here, same thing, carbon, hydrogen, and oxygen. And we have 1 carbon, 2 hydrogens, and 3 oxygens here. And on the other side, 6 carbons, 12 hydrogens, and 8 oxygens. And that's because it's 6 plus 2, right? 6 here and then 2 here. So I'm writing that like that on purpose, showing the addition so that when we get ready to balance it, we can just change these numbers to whatever the new number is, and then we'll know how many oxygens we have. So let's start out by balancing the, carbons. Let's do that. So I have 6 carbons on this side. What coefficient should I put here to balance that? Keep in mind, sometimes this is trial and error. So sometimes you might put a coefficient in that doesn't work. It might work initially, but then you start changing the amounts of the other atoms. And so then you have to go back and do something different. But for now, what would you start with?
Maybe 6.
6, right? We got 6 carbons on the other side. Let's put a 6 in here. And let's see what that gives us. So that's gonna increase this. So now you got 6 carbons. It's also gonna increase this. So let me write that as 2 plus 1. But now with the 6, now this becomes 6 times 2. So that's gonna be 12. And then this oxygen right here is gonna be 1. So that's gonna be 13. So this is now 12 plus 1, and that's 13. Right, so 12 plus 1 oxygens. Initially you had 2 plus 1, so you had 3. Now you got 12, because that 6 is going to distribute through to both carbon and oxygen, which has a subscript of 2. So now it's that's 12 and then plus 1. Now let's try balancing the hydrogens. All right. So now let's take we got 12 on this side. So we want to make it 12 on this side. So we're going to put another 6 here. And that's going to be 6 times 2. So that's going to give me 12 hydrogens. Right? Everybody okay with that? It's also going to distribute through to oxygen. So now we're going to have 12 plus what?
6.
12 plus 6. So that's the number of the final number of oxygens on the left side, on the reactant side. On the other side, now I have, this is fine. I got 6 carbons, so that's balanced on both sides. I got 12 hydrogens, that's balanced on both sides. Now I need to balance the oxygens. I have 8. I need 18. What can I do? What would you, so how many more do I need if I have 6 right here, and I don't want to put a coefficient in front of that number if I don't have to, because that's going to throw all of my other numbers off. But I have this oxygen sitting out here by itself. So I can touch that to alter the number of oxygens. So what would you do if I got 6 here already and I need 12 more. What could you do?
Put another 6 in front of the O2.
Put another 6, put a 6 right here. And now this becomes 6 plus 12 because that is going to distribute to the subscript. All right, so that's going to go from 2 to 12, and then that's going to give me a total of 18 oxygen. So now my oxygens are also balanced. So the overall total balanced equation is 6 mole. And I'm saying this in terms of what these numbers mean. So 6 moles of CO2 plus 6 moles of water gives me 1 mole of C6H12O6 and then 6 moles of oxygen gas. That's how you look at those coefficients. Those are, again, let me change them. These are my stoichiometric coefficients. Right? And these numbers tell me my relationships between the atoms or molecules that are reacting and the products that are formed. And they also tell me the ratios of each one of those, right? That's how they exist in a specific or relative number based on those coefficients. All right. So let's take 2 word problems and work through those because they bring a lot of skills into play as well. Man, where did I put that? Hold up. Take a page out. I don't think I did. Maybe I screwed up somewhere. Hold up 1 second. We can fix that. Let me grab these pages. Where am I? I'll just. Okay, hold up. I screwed up some kind of way. I didn't import the right pages into your document because I use 2 different documents. So let me do this. Let me add these. Let me pause the recording again. All right. So we're going to do, and we've already done the other problems anyway. So we're going to do this problem right here, where we have to take the words and turn them into an equation. That's a skill. We're also going to figure out from this, we're also going to balance it. And we're also going to figure out like some other stuff too. So let's take it. So copper is telling me that I'm using copper, which in this case, unless it tells me that it's a copper anion or a copper ion, that is elemental copper. All right, so I'm just going to use that. So that's just going to be Cu. All right, and then it's going to be plus sulfuric acid, which is H2SO4. You need to commit that one to memory. You're going to see that a lot. So sulfuric acid, those two come together to form copper 2 sulfate. And then water. And sulfur dioxide. Now notice on this question, we do see the sulfate polyatomic by itself intact on both sides, but we don't see this on both sides. That's only on the right side. So this one, we're gonna have to balance atom for atom. We're not gonna keep the polyatomics together and balance them separate. Balance them as they are. We're gonna balance the polyatomics separately. Now, if we look right here, it says copper 2 sulfate. What does that mean? What does the 2 in parentheses mean? When you have a name written like that and you have a Roman numeral in parentheses, what does that tell us about that compound? Or what does it tell us about the metal? Because it does tell us something. And if we answer that correctly, then you'll be able to answer the next question that I'm going to ask. Anybody? What does that parentheses, Roman numeral in parentheses tell us about copper?
Aren't there like two types of copper though? Like,
Yes.
so it tells you which one it is.
You're right. So that tells us when we say type, what I think what we need to say is that copper has 2 different oxidation states. So this is telling us that this is copper 2 plus. If that was 1, it would mean that it was copper 1 plus. So copper, so that Roman numeral tells us the oxidation state. Of copper, which is 2 plus in this case. Right. So if copper is 2 plus, let me see how you're thinking. What's the charge on the sulfate anion? If both subscripts, I'm going to put this in parentheses, by the way, so we can. If both substrates, you know, those ones are understood. I'm just putting them there for emphasis. If both substrates have a subscript of 1, what is the charge on the sulfate?
-2.
It's -2. Good. And the reason I'm saying that is because we can't forget those polyatomics. You're going to see those things from here until forever. So always keep going back and refreshing yourself on those polyatomics. Keep going back and touching up on that because you're going to see them and you're going to be expected to know the charges and the names and all of that. So you need to keep even if you're studying another topic, you can still go back, take 5 or 10 minutes and look over that list that I gave you of polyatomics. All right. So, but the reason I'm saying that is because you will never not see polyatomics from this point forward in this class. You're going to always see those polyatomics. All right. So the sulfate is -2, copper is 2 plus. If copper was 1 plus, that would be a subscripted 2 next to it, but it's not. And so we need to be able to work through those nuances as well. All right. So now let's go ahead and balance this thing. We got we got 1 copper. All right, we got 1 copper. We got 2 hydrogens. And we have 1 sulfur and 4 oxygens. Right. And then on the other side, we have 1 copper. We have 2 sulfurs. We have 4, 5, 7 oxygens. And we have 2 hydrogens. Let me move that down. All right. So let's start out by trying to balance the sulfurs. Let's balance the sulfurs. All right. So we got on the other side, we got 2 sulfurs on the product side. So on the reactant side, let's do this. Let's take this sulfur and let's put a 2 here. All right. Let's put a 2 there. What's that? What does that do to the hydrogens?
Makes it into 4.
So you got 4 hydrogens. Good. Now you have 2 sulfurs, and then this is going to distribute to oxygen as well. Since there's a subscript 4, that's going to be 4 times 2. So now you got 8 oxygens. All right. Now on the other side, we need to balance. Let's balance the hydrogens. And in doing so, what we're going to find out is that we're also going to be able to balance out the oxygens, and the copper is not going to change, and the sulfur is not going to change. So let's balance out the hydrogens now on the other side. So over here, I'm going to put a 2 here, right? That's going to change this to 2. And it's going to change that oxygen. Let me show you here. Let me break this out because that 7 is kind of misleading. You have 4. It was 4 plus 1 plus 2. Are y'all following? 4 from the SO4, 1 from the water, and then 2 from SO2. So now if I take that water and multiply it by 2, I'm going to get 4 hydrogens. And then this number, which was from the water, I'm going to multiply that by 2. So now I'm going to have 4 plus 2 plus 2, which is going to give me a grand total of 8. Sometimes when you see those odd numbers, initially it makes you, want to jump to use a fraction or something like that. But in this case, you didn't have to do that, right? Is everything balanced now? That's the question. So 8 and 8, 2 sulfurs, 4 hydrogens, and then 1 copper. Is that right? All right. So that's again, those word problems call for you, and we're gonna do more of these on Thursday. But they call for us to know how to go from name to compound. So from the name to the molecular formula, right? Or the ionic formula. And that's the purpose of doing those types of problems, is to make sure that we're able to do that. All right, we'll do some more of those on Thursday. Now I want to add in another topic. Let me move this, and I'll straighten all these notes up before I upload this stuff. But now I want to talk about another topic dealing with writing and balancing equations, and that is the topic of net ionic equations. So let's introduce that real quick while we're talking about balancing and ions and all of this stuff. Hold up, what did I just do? Right. So when we talk about the net ionic equation, when we do a reaction, if it's not neat, you do it in a medium. And so if the reaction itself is done in water, or if it's done in an aqueous solution, then a lot of times when you add in the ions, or when you add in the compounds, they actually break up into their respective ions. So when you talk about a net ionic equation, what you're looking for in this case is a reaction that's done in aqueous medium. aqueous is just a fancy term for water, right? So if you dissolve everything up in water, then you're able to generate what's called a net ionic equation. So normally, if you take an ionic compound, like let's say calcium chloride, and you dissolve it up in water, right? This is going to dissociate. Notice I took the subscript here and I maintain that number of chlorines here. So when these ionic compounds break up into their ions, this is called dissociation. I'm gonna put this in quotes because that's not a technical term. Right, but a lot of times if you dissolve up an ionic compound in water, the water can kind of get between the ions, and that's why it's able to dissociate like that. Right. So we're gonna take an equation and we're gonna look at how to get to the net ionic equation, because the net ionic equation is basically looking at all of the ions in solution, canceling the ones that are common to both sides, and then writing out the equation with what you have left. Right, so let's look at that. So let's take an example. Excuse me. You have calcium chloride, and then you have silver nitrate, and that's going to give us calcium nitrate and silver chloride. So this type of reaction, we call this a double displacement. Right? That's a fancy phrase. All it means is that the partners are swapping places. So the cations and anions swap with each other. Let me put this in here. Right? So let's balance this real quick first, and then I'll show you what I mean by cations and anions swapping. All right. So is this balanced as it is? What would we need to do to balance it?
The NO3.
Yeah, let's balance that. So what will we put here? A 2? That'll give us 2 NO3s on both sides. Is that right?
Yes, sir.
And then 2 silvers. So now we got to balance the silver. So if we put this here, that's going to give us 2 silvers, 2 chlorines. And then over here, we already have 2 chlorines. The calcium is the same on both sides. So we're good. All right, we got 1 calcium on each side. We got 2 NO3s on each side, 2 chlorines on each side, and 2 silvers on each side. Right? So when we take that and this is going to be a solid. Right? So when we break this up, that's going to stay intact, because if it's solid, if a solid is formed, that means it's not soluble. So it's not going to be dissociated. If it's in the product. Right, I'm just saying this for later. So if you have a solid in the product, it's not dissociated. So you leave it as it is when you write the net. Right. So let's think about this in terms of I might just put a page in here. All right, let's think about this in terms of the ions that are involved, right? So we're going to write this out. So this is the molecular form. Let's write it out in this ionic form. In other words, we're going to break all the ions apart. And you'll see what the double displacement part, where that comes in. So this is going to be Ca 2 plus plus 2Cl minus, because I'm just taking that subscript and making sure I stay true to those numbers. And then it's going to be plus 2Ag plus 2NO3 minus. That's on the reactant side. On the product side, we're going to have Ca 2 plus, and then I'm going to keep this subscript and turn it into a coefficient. So now it's going to be 2NO3 minus. All right, and then since the silver doesn't dissociate because it's a solid, I'm gonna leave it. And the reason I know that it doesn't dissociate is because of my solubility chart, which we're going to talk more about on Wednesday. Right. So anytime you have a chloride and it reacts with silver, it's going to precipitate. It's going to be a solid. All right. So here, let's go back to here. This is the ionic equation. What you'll notice, and let me put the state here. This is a solid. What you'll notice is that the calcium here and this is, let me fix that so you don't think it's copper. The calcium here is the same on both sides. And then here, the nitrate and the nitrate is the same. So those are what you call spectator ions. So calcium those are spectators. So we want to remove those to write the net ionic equation. Right, so I want to get rid of the spectators. So I'm just going to line through them. So this is the same on both sides. Right, so this is the molecular with everything together, the ionic with everything broken out into its respective ions, and then the net ionic is going to be here. Right, it's kind of like gross pay and net pay is what's left over. All right, so it's 2 Ag plus 2Cl minus going to Ag, and need to put that number back in there. 2 AgCl. All right, this is the net ionic equation. And since all the coefficients are the same, we can just write it as Ag plus Cl minus going to AgCl. All right. Questions about that part? So again, this is really important to know your charges on your polyatomics. When you break these things apart, you got to know your charges, but you can tell what the charge is based on the subscripts in the formula itself, right? So that helps, because if we apply that crisscross method, then we know how to break it apart and take the subscripts and turn them into the charges on the polyatomics. All right. So we're going to stop here. We'll pick this up on Wednesday. I'll clean these notes up before I post them, and then make sure everything is good with that. And then, yeah, we'll come back on Wednesday, God willing.
Thank
You
you.
have a great day. Bye.